Okay, everyone. Today I'd like to show you how to solve this problem number 4 in chapter 9 of Sheldon Axworth's third edition of Linear Algebra Done Right. This is in the inner product spaces chapter. And inner product spaces are really just a generalization of the dot product to function spaces in general, to functions in general. So it's a real and complex valued functions. So suppose V is a real inner product space. Show that for all vectors u and v in the vector space capital V, that the inner product of u plus v and u minus v equals the difference in their magnitudes, magnitude squared. Now show if u and v have the same norm, then u plus v and u minus v are orthogonal to each other. And finally use part B to show that the diagonals of a rhombus are perpendicular to each other. Okay, so the first part of the problem, u plus v and comma u minus v. The big thing you need to know when dealing with vectors inside an inner product operator is that you simply operate the same way you distribute two numbers, and we use distributive property of multiplication. So this inner product simply becomes these four terms expressed over here. Now, inner products follow two properties: commutativity, meaning the order that you have the vectors in the slot doesn't matter, and then homogeneity. If you have a negative sign, you can factor it outside the operator. So given this v comma u, bracket v comma u equals bracket u comma v, and then the u comma minus v bracket simply becomes minus outside. These two terms in the middle are now the same, so they cancel out. And this becomes a negative term. Now you're just left with inner product of u with itself and v with itself, and inner product of a vector with itself simply equals the magnitude squared by definition. So we immediately end up with this final step here that, well, you get the difference in the magnitude squares of the two vectors. So that answers problem number 1. Now problem number 2 is very easy because it states that what happens if the norms of these two vectors are equal? Well, based on this equation, if v, magnitude of v squared were to suddenly become magnitude of u squared, this would cancel out to become 0. And so you would get that inner product of u plus v and u minus v equals 0, which is the exact definition of orthogonality we have for inner product spaces. Now, how can we conclude that this means that the diagonals of a rhombi are perpendicular to each other? That's simply for, if we take a look at the Euclidean space of R2, we can see this just by manipulating vectors around in tip-to-tail addition. So you have a vector u and a vector v. You just simply add them tip to tail using the parallelogram law. That's u plus v. U minus v will be in the opposite direction. If you aren't clear as to why u minus v is the case, you could always imagine if this is vector u, you have a vector u here, and then minus v is the opposite of this vector v, which is in this direction, which gives us this vector. Now we are allowed to go and displace this vector anywhere we want. It's the same vector. Vectors do not care about your position or location on the coordinate space. All that really matters is the magnitude and the direction. So vectors u and v will span out an arbitrary quadrilateral, but we know that this must be a rhombus if the two vectors have the same length. And given we know that u plus v and u minus v vectors must represent their diagonals, since we concluded that they're perpendicular to each other, then indeed the diagonals of a rhombus must be perpendicular to each other in R2 at least. And so that concludes the problem. Please let me know if there are any tips I can do to improve the quality of these videos, and if there are any particular problems you'd like to see. I'm thinking of doing a linear algebra done right list um, of several videos in the future. But that's essentially it. Hope you enjoyed the video. Thank you.